The AI chip race has spent years chasing one goal: more computing power. Cerebras now says that is no longer enough. Its new CS4 system is built around a different argument. The future of AI will be decided not only by how much intelligence a machine can produce, but by how quickly that intelligence reaches the user. Cerebras claims CS4 can deliver AI responses at up to 30 times the per-user speed of GPU-based systems, while dramatically improving throughput per watt. If that performance holds up across real production workloads, it could challenge one of the assumptions that made Nvidia dominant, that scaling AI means connecting more and more conventional chips together. The CS4 looks unusual because the processors inside it are unusual. Instead of relying on many relatively small GPUs, one CS4 rack contains 3 WSE3 turbo processors. Each of these chips is essentially an entire silicon wafer turned into one processor, covering about 46,225 square millimeters, and containing roughly 4 trillion transistors and 900,000 AI-optimized cores. Conventional semiconductor manufacturing normally cuts a wafer into hundreds of individual chips. Cerebras takes the opposite approach. It keeps almost the entire wafer together. The objective is to reduce one of the biggest hidden costs inside modern AI systems: moving information between separate processors. That movement matters because large AI models rarely fit neatly inside one conventional GPU. Their parameters are distributed across many accelerators, and those accelerators must constantly exchange data while generating each token. Every transfer consumes energy and introduces delay. Imagine a factory where one worker can perform only part of a job, so the product must repeatedly travel across the building between different departments. Making every worker faster helps, but the conveyor belts eventually become the bottleneck. Cerebras tries to remove much of that internal transportation by placing an enormous number of cores and a large amount of memory bandwidth on one continuous piece of silicon. This architecture is particularly relevant to inference. Training is the process of teaching a model. Inference is what happens afterward, when the trained model actually answers a question, writes code, generates a report, or performs an agentic task. During the first stage of the AI boom, training captured most of the attention because laboratories were building increasingly large models. But the economics are now shifting toward inference. A model may be trained once, then used billions of times. Every chatbot response, coding agent step, AI search query, or autonomous workflow becomes another inference job, and inference has a different performance problem. A data center operator does not care only about total tokens produced across an entire cluster. Users care about how quickly their own answer appears. If a system can generate enormous aggregate throughput, but each individual user waits several seconds between pieces of a response, the experience still feels slow. Cerebras is therefore emphasizing a metric called tokens per second per user. On one comparison using the GPT-OSS-120B model, Cerebras says CS4 exceeded 4,400 tokens per second for an individual user and was up to 30 times faster than GPU-based alternatives under the company's stated test conditions. That figure comes from Cerebras itself, so it should be treated as a vendor claim rather than an independent universal benchmark. The difference becomes more important when AI turns into an agent. A normal chatbot may generate one response and wait for the next question. An agent can perform dozens or hundreds of sequential operations. It might inspect a software repository, decide which file matters, write code, run a test, read the failure, revise the code, search documentation, delegate a task to another agent, and then verify the final result. Many of those steps depend on the output from the previous one, so they cannot all happen simultaneously. Latency accumulates. If each reasoning step takes 5 seconds, a 100-step workflow can become painfully slow. Reduce that delay dramatically, and the same agent can complete much more work within the same wall clock time. Cerebras CTO Sean Lee argues that this is why speed changes the product itself, rather than simply improving a benchmark. A system with much faster token generation gives an agent more time for reasoning, verification, and tool use before the user loses patience. that could create a new kind of competition in AI infrastructure. Nvidia has spent years optimizing for massive parallel throughput across GPU clusters. Cerebras is trying to make sequential inference fast enough that autonomous AI feels interactive even when the model is doing substantial work behind the scenes. The CS4 also represents a major redesign of Cerebras hardware around the wafer-scale processor. Previous systems already used large wafer-scale engines, but the new Nexus architecture separates the rack into modular compute, power, and input-output components. Reuters reports that Cerebras reduced the overall component count by around 50%, partly to make systems easier to manufacture and deploy inside data centers. This matters because exotic hardware can lose its performance advantage if it is too difficult to install, service, or scale. Nvidia's greatest strength is not merely that it makes fast GPUs. It has spent years turning those GPUs into complete racks, networking systems, software stacks, and deployment standards that data center operators understand. Cerebras is now trying to solve more of that operational problem. Power delivery is another part of the design. Cerebras says the Nexus architecture moves power conversion much closer to the processors than conventional GPU boards. The company claims this reduces board-level power losses and allows roughly twice as much power to reach each WSE3 turbo, increasing operating frequency and token generation speed. The result is not a brand new manufacturing node. The WSE3 turbo is still fabricated using TSMC's 5-nanometer process. Much of the performance gain comes from system engineering around the processor, rather than simply shrinking the transistors. That is important because the semiconductor industry is increasingly learning that chip architecture alone cannot solve every problem. Modern AI systems are becoming rack-scale computers. Power delivery, cooling, networking, memory placement, and software determine how much of the theoretical processor performance becomes useful work. Nvidia has moved aggressively in the same direction with tightly integrated systems. AMD is doing the same. Cerebra's Nexus platform shows that even a company built around one radically different chip must now compete at the complete system level. According to Cerebras, a CS4 rack provides 750 petaflops of AI compute, 7.2 terabits per second of input-output bandwidth, and 129.6 petabytes per second of memory bandwidth across its 3 wafer-scale processors. The company says wafer-to-wafer latency can fall to around 2 microseconds, and that large clusters can support models exceeding 50 trillion parameters. These are extraordinary specifications, but raw numbers alone do not determine whether a system succeeds commercially. Customers care about model compatibility, reliability, utilization, price, energy consumption, and how difficult it is to move existing workloads onto a new architecture. Nvidia's CUDA ecosystem has become one of the strongest competitive advantages in the technology industry. Developers have spent years building applications, libraries, debugging tools, and optimized kernels around Nvidia hardware. A competitor can create a processor that looks better on paper and still lose because moving real software is expensive. Cerebras must convince customers that its inference stack can run the models they actually use without creating an engineering project larger than the performance benefit. The company has already been working to address that problem by serving major open models on its cloud and supporting models with very large parameter counts. Its architecture can distribute model weights across multiple wafer-scale systems when necessary, but the fundamental trade-off remains. A huge processor can keep more computation physically close together, which helps latency, but each wafer has a finite amount of directly integrated SRAM. Extremely large models still require clusters and external memory systems. Semi-analysis notes that reusing the WSE3 generation means CS4 does not completely remove the memory capacity trade-offs inherent in Cerebras's architecture. There is also a manufacturing question that would have seemed impossible 2 decades ago. Conventional semiconductor economics are built around cutting wafers into smaller chips because manufacturing defects occur randomly across the silicon. If one small die contains a serious defect, the manufacturer discards that die while keeping the rest. A wafer-sized processor cannot simply throw away one tiny region. Cerebras had to design redundancy and fault tolerance into the architecture so defective cores and interconnects could be bypassed. The company argues that this allowed it to make full wafer processors economically viable despite the defect problem that historically prevented the approach. Now, the company wants to scale that unusual architecture far beyond a few specialized installations. CEO Andrew Feldman told reporters that Cerebras expects to deliver about 600 megawatts of computing capacity by the end of 2027. He said the engineering roadmap is intended to make the company's systems around 4 times faster by the end of this year and deliver roughly 20 times more throughput by the end of 2027. Cerebras also plans another generation of processor and server hardware next year. These are aggressive targets, especially for a company competing against Nvidia's enormous manufacturing ecosystem and purchasing power. The financial context makes the challenge clearer. Cerebras reported an adjusted loss of $6.9 million on $180.1 million in sales in its latest quarter. That revenue shows the company has real customers, but it remains tiny beside Nvidia. Nvidia can invest tens of billions of dollars across chips, networking, software, financing, and supply agreements, while using its massive revenue base to secure manufacturing capacity. Cerebras does not need to replace Nvidia across the entire AI market to succeed, but it does need to prove that its architectural advantage creates enough value to justify adopting a much smaller ecosystem. This is where inference may offer the best opening. Training frontier models rewards flexibility and compatibility because researchers constantly experiment with new architectures. Inference is often more stable. Once a company knows exactly which model it needs to serve, it can optimize aggressively around that workload. If Cerebras can provide much faster responses at acceptable economics, customers may be willing to use its systems for serving models even if training still happens elsewhere. The rise of reasoning models makes this opportunity larger. AI systems increasingly generate internal chains of computation before producing a final answer. Coding agents perform repeated loops. Research agents search and verify information. Future agents may coordinate other agents. Each improvement in reasoning quality can create more inference demand because the model performs more work per user request. The industry could therefore enter a period where the limiting resource is no longer only how many models can be trained, but how quickly billions of complicated inference sequences can run. This also changes the meaning of power efficiency. Data center operators are running into electricity constraints around the world. Grid connections can take years. Transformers, substations, and transmission lines are becoming strategic resources. If one architecture can generate substantially more useful work within the same megawatt, the operator effectively creates additional computing capacity without securing another power plant. Again, that is a company claim and will need to be evaluated across independent production workloads, but the direction reflects where the entire industry is going. Performance per watt is becoming as important as raw performance. There is a deeper reason this launch matters. For decades, the semiconductor industry assumed that large computing problems should be solved by connecting more individual chips. Cerebras is testing the opposite extreme: make the fundamental processor physically enormous, keep as much communication on silicon as possible, and then connect a smaller number of those giant processors together. Neither approach is universally superior. The right answer depends on model size, software, memory requirements, reliability, price, and workload characteristics. Nvidia's architecture has already proven that networks of GPUs can create one of the most valuable computing platforms in history. Cerebras is trying to prove that inference creates a specific weakness in that model because moving data between many separate processors imposes latency that becomes visible to users. If AI remains mostly about generating a paragraph of text, the difference may not matter enough. If agents spend minutes reasoning through hundreds of sequential steps, every fraction of a second becomes much more valuable. That is why CS4 should not be viewed simply as another chip trying to beat Nvidia on a benchmark. It represents a bet on what artificial intelligence is becoming. Cerebras believes the next stage will reward infrastructure that makes very large models feel instantaneous and allows agents to think through more steps without making users wait. The first AI race was about training the largest models. The second was about deploying them cheaply. The next one may be about making intelligence fast enough that machines can reason, verify, and act in real time.